Good afternoon, students. The total only 400 students are there. Yeah, today I'll be starting the new programming model, which are calling as a dynamic model or dynamic programming model. What is the prerequisite for this particular dynamic programming model is we should aware of divide and conquer model as well as the greedy model, which is covered in previous classes. So if you look at the previous models, like if you take a divide and conquer technique. So in the divide and conquer technique, the problem is recurringly we are dividing into a subproblems. So by dividing the problem into a subproblem, we are reducing the complexity of that particular problem. At one particular stage, at one particular subproblem, the problem is so simple, you can easily solve it. For example, if you take a merge sort or a quick sort, the entire list of elements are divided into a sublist. So how long you are performing a division is, if the list contains only one element, you are saying it is a small problem for us. So it means if a list contains only single element, it means the list itself it is in sorted order. Any list if it contains single element, that list itself it is in sorted order. So that is the benefit we are getting when you are dividing the problem into a smaller problem. Okay. So that is what a divide and conquer technique that we learn. We solved many problems which comes under a divide and conquer technique. In the similar guidelines, there is another strategy we are calling as a dynamic programming, used when problems breaks down into recurringly small subproblems. Like similar to your divide and conquer, in dynamic model also, the problem is divided into a subproblems. Okay, so this is the first point you have to remember. This one. Okay, so dynamic programming is a typically applied to optimization problems. In such problems, there can be many solutions. Each solution has a value, and we wish to find the solution with an optimal value. Okay, so by using this dynamic model, we are getting many solutions, like in greedy model, how you are getting a many feasible solution. Here also we are getting a many feasible solution, and we need to find the optimal. Okay, so there are two strategies are there here I am talking. One is a divide and conquer model, the other one is a greedy model. Okay, we see how the dynamic programming is different from these two models also. So as a part of the introduction. Yeah. So let me just go through the 2-3 slides which are there. So dynamic programming is a general algorithm design technique for solving problems defined by or formulated as a recurrence with overlapping subinstances. Okay. So what do you mean by overlapping subinstances is, like in divide and conquer model, whenever you are dividing the problem into a subproblems, all these subproblems are a disjoint subproblems. But whereas here the subproblems will repeat in dynamic model. The subproblems, the whatever subproblems are there, when you are dividing the problem into a subproblems, these subproblems will arise repetitively. Okay, so anyhow I will be taking one example, so there you can understand what exactly this overlapping of subinstances. Okay. So invented by American mathematician Richard Bellman in 1950 to solve the optimization problem. Okay, so divide and conquer model is not used for solving the optimization problem, but whereas this dynamic model is used only for solving the optimization problem. Okay. So the main idea is here, set up a recurrence relating a solution to a larger instances to solutions of some smaller instances. So larger instances solutions are converted into some smaller sub-instances. Solve smaller instances once. Record solutions in a table. Extract solutions to the initial instance from the table. Okay. So these steps you can easily understand when I am taking one simple example. Okay. A dynamic programming is a way of improving an inefficient divide and conquer algorithm. Okay. So by inefficient, we mean the same recursive call is made over and over. So actually in divide and conquer model, all the subproblems are disjoint subproblems. So you will be solving individually. But whereas when you are dividing the problem and if the subproblems are overlapping, so why to solve the same problem several times? Okay, so if you apply a divide and conquer model and if you are getting a subproblems which are repetitive in nature, then no need to solve the same problem many times, which is occurred in divide and conquer model. Okay, so to overcome that one, so we are solving one time in dynamic model and we are using many times. We are using many times. Okay, so that is what the meaning of inefficient. If same subproblem is solved several times, generally it occurs in divide and conquer model. If the subproblems are overlapping, we can use a table to store a results of the subproblem the first time it is computed and thus never have to recompute it again. Okay. So dynamic programming is applicable when the subproblems are dependent, that is when subproblems share the subproblems. Okay. So that repetitive nature you will be understanding. Some of the elements of a dynamic model. So dynamic programming is used to solve the problems with the following characteristics. Simple subproblems, the first one, we should be able to break the original problem to a smaller subproblems that have the same structure. That is what a division. And optimal substructures of the problems. The optimal solution to the problem contains within optimal solution to its subproblems. Okay, suppose I want to find the optimal solution of a given problem. In order to solve that particular one, and when you are performing a division, whatever that subproblems are there, so that subproblems also be the optimal subproblems, optimal solution of the subproblems. Okay, so that is what the principle of optimality says. Okay, so that next slide it will be there, the definition of the principle of optimality. So overlapping subproblems. If overlapping subproblems are not there, then the dynamic no use. It is just like a divide and conquer model. Okay. So there exist some places where we solve the same subproblems more than once. So the benefit of dynamic model is the same subproblems are repeated. So in this case, we are solving only first time. Then we are reusing the same results to other same similar subproblems. The dynamic programming works on a principle of optimality. This is very important. So generally when you go to any interviews, they will be asking what exactly the principle of optimality. Okay. So principle of optimality states that in an optimal sequence of decisions or choices, each subsequence must also be the optimal one. Okay. The meaning of principle of optimality is, suppose if you let us take a general example from let us city A to city B via city C. From city A to city B via city C is an optimal solution. A to B is an optimal via C. Let us define once again. Let us city the distance between or the cost between city A to city B is an optimal one via C. Then from city A to C and city C to B is also a suboptimal. So the principle of optimality states that if A to B via C is the optimal sequence of decisions, then from A to C is also a optimal sequence of decisions. Because in between this one, so there is D1, D2, like this, many decisions are there. So here also some C1, some E1, E2, like this, there are many sequence of decisions are existed between A to B via C. Okay. So here the principle of optimality is saying that if A to B is a optimal via C, then A to C also optimal as well as C to B also it is optimal. If you are taking as a distance, if the A to B is a distance is optimal via C, then definitely from A to C also the optimal distance and C to B also a optimal. Okay, so this is mandatory. If A to C is not a optimal one, then there may be some other way where it is optimal, and then the overall also will reflect. So that is the meaning of the principle of optimality. So by using the principle of optimality, we can identify the optimal sequence of decisions. Okay. So that is what the definition of the principle of optimality. So I'll be taking the same thing with the help of the example. Don't worry about these terminologies. Okay. Yeah. In order to understand your dynamic programming model, I have taken one simple algorithm, simple problem. Okay. So with the help of this, I am trying to explain how dynamic programming works. Okay. Yeah. So in order to explain the particular one, I have taken the Fibonacci number. Okay. So what is the Fibonacci sequence? You know that one. So it is the Fibonacci sequence is nothing but 0, 1, 1, 2, 3. So like this you will be getting the numbers. So the current term, if you want to find the current term, it depends on the previous two terms. Okay. So that is what the Fibonacci series. So I write a small algorithm here. If n equals to 0 or n equals to 1, then return n. Otherwise, return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay. So this actually comes under a divide and conquer model. So whatever algorithm I wrote it is under divide and conquer. Okay. So how it is comes under divide and conquer is, if I want to find the nth Fibonacci number, is depends on the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. Okay, so here if n equals to 1 or if n equals to 0, it is a small for us. It is a small for us. Otherwise, it is a big, and the same problem is reduced the time complexity by reducing the n minus 1 and n minus 2 values. Okay, so you just look at this algorithm. So the condition, the whatever condition is there, this is what a small condition in the divide and conquer. If it is not a small, the same problem is divided into sub-problems. One is finding a Fibonacci of n minus 1 term plus finding the Fibonacci number of n minus 2. Okay, so let us look at how this function calls occurs. So when I am calling the Fibonacci of 6, I want to find the sixth term of the Fibonacci. Okay, so when I first invoke the Fibonacci of 6, so internally the Fibonacci of 6 means the 6 is not a small here, the 6 is a big for me, so it is divided into again two sub problems, that is fib of n minus 1 and fib of n minus 2. Suppose I want to find the Fibonacci of 6, so I need to compute a Fibonacci of 5 and Fibonacci of 4. Is it clear? This point is clear for everyone? Any questions from your side? Okay, no question. See here, try to understand this particular problem. Okay, in order to find the Fibonacci of 6, I need to compute the Fibonacci of 5 and Fibonacci of 4. It is a recursive. It means the problem with n equals to 6 is divided into two parts. The left side you are finding the Fibonacci of 5 and the right side you are finding the Fibonacci of 4. Similarly, the Fibonacci of 5 again it is divided into two parts, that is Fibonacci of 4 and Fibonacci of 3. Similarly, in the right side also the Fibonacci of 4 is again divided into a Fibonacci of 3 and a Fibonacci of 2. So the same function Fibonacci of 6 is divided into 5 and 4. Here the 5 and 4. So it means if I want to compute the value of Fibonacci of 6, this value, I must compute the Fibonacci of 5 and Fibonacci of 4. Again, in order to compute the Fibonacci of 4, once again I am calling Fibonacci of 4 and Fibonacci of 3. Similarly, for to compute the Fibonacci of 4, and we are invoking Fibonacci of 3 and 2. So like this, again if we expand the tree, here again to compute the Fibonacci of 4, so we need to compute again 3 and 2. Similarly, Fibonacci of 3, again it is 2 and 1. So I once again get for 3 for this one, again 2 and 1 for this one, 1 and 0. So like this, again further we expanded this particular tree. So how long you are expanding the tree? Until the problem is become a simple. So when the problem is become a simple is n equal to 0 or n equals to 1, then only it is a small for us. It gives the results. Otherwise, it is dividing like that only. Okay. So here still it is further divided. Still it is further it is divided. Okay. So this is what the complete tree. This tree will tell you that how many times the Fibonacci function is invoked. Initially we invoked with Fibonacci of 6. So that is invoked Fibonacci of 5 and 4. Again 5 is invoked as a 4 and 3. So like this is recurrently it is invoking the Fibonacci function. Okay, so this is a simple algorithm. You can easily understand. Okay, so here how long it is expanded is you can just look at the leaf nodes. In the leaf nodes, whenever n is become a 0 or whenever n equals to 1, then immediately it returns the value. It returns that value. So here initially you are invoking with Fibonacci 6, then you are invoking Fibonacci 5, You're invoking Fibonacci 5 first, then Fibonacci 5 once again it is invoking Fibonacci 4. See here, it is just I am looking how the function calls are occurred. So first it invokes the Fibonacci of 6, that is we are invoking from the main function. Then Fibonacci 5, the first one, the first line here, this one, this will be invoked. Again the same function Fibonacci of 5 is invoking Fibonacci of 4. Again Fibonacci of 4 is invoking the Fibonacci of 3. Again Fibonacci of 2. Then followed by Fibonacci of 1. So when you are invoking the Fibonacci of it returns the value 1. So then that value you are receiving. So after invoking Fibonacci of 1 at which location? This location. All of you see it, this location. After Fibonacci 1, the same Fibonacci 2 is invoking Fibonacci of 0. So the value returns is 1 and 0. Then after this, which function is invoked? This function is invoked. Because in order to find the Fibonacci of 3 here, so the left part of is over, that value is written by this one, this value returns here. Then it invokes the Fibonacci of 1. Again you are getting the value. So after this one, which one is invoked? Again this one is invoked. So this is what the sequence which will follow. Okay. Then after this one is invoked. Then this one will be terminated. Again this one will be terminated. And again this one will be. So like this, after completion of all the left part, so just I am traveling in order. It is nothing but I am traveling as in order. Okay. So after completing the left side, then the right subtree I am coming. So once again you are invoking the Fibonacci of 4. Again 3, 2, 1 terminates, 0 terminates, 1 again terminates, invoking 2. Okay. So like this, you are invoking the Fibonacci function recursively. This is how your program flows. Of course, the background it uses a stack there to do all these things. What is your observation in this one? So in order to compute the Fibonacci of 6, we need a value of Fibonacci of 5 as well as we need a value of Fibonacci 4. Okay. So because Fibonacci of 5 value we don't know and 4 is also we don't know. So again you are expanding. So when you are expanding, you can observe that how many times we invoked a Fibonacci function with the same values. Like if you take a Fibonacci of 6, so Fibonacci of 5 is invoked only one time. First time it is invoked, then we need to compute that particular one. But whereas when you are invoking the Fibonacci of 4, how many times you are invoking? 2 times you are calling. When you are calling the Fibonacci of 4, then if you call 100 times, it will give the same value only. So why to call 2 times? Here 1 time, here another time. So why we need to call the same function 2 times? Let us call the first time when you require the value and store that value in a table. Like whenever you are calling the Fibonacci of 4, you can replace by using that value. You need not invoke several times the Fibonacci of 4. Here you are invoking it 2 times, which is not required. So, and what is the other point you need to observe is the Fibonacci of 4 is the same subproblem which is repeated. That is what overlapping. That is what overlapping actually. Okay. Again, if you look at the Fibonacci of 3, see how many times you are invoking Fibonacci of 3? 3 times. So why 3 times it is required? So one time you invoke it and use the same value for other purposes. So first time you find the value of a Fibonacci 3 and use the same value for this one, so that the function calls are drastically it is reduced. Okay. So similarly, when you take Fibonacci of So when you take Fibonacci of 3, so how many 3s are there? So many are there. This is 3 over. Next, look at the Fibonacci of 2. How many times? 1, 2, 3, 4, 5 times you are invoking the Fibonacci of 2. So one time call the function, use remaining 4 times that one. Okay. So that is what you need to do. Yeah, once again, if you look at the Fibonacci of 1, how many times you are calling? 1, 2, 3, 4, 5, 6, 7, 8. Like this, several times you are calling the same function. Yeah, yeah, you can look this particular one. Like there is a colors I have given for every this thing. You can observe these values. Okay. So instead of invoking the several times, okay, you observe here. So if I know the Fibonacci of 4 here, the whatever that value I am getting for Fibonacci of 4, this value, I can simply substitute here. Suppose this value is x. If this value is x, then same value I can use it. It means I need not invoke all these function calls to find the, see how the time complexity is reduced. So almost 50% of the time is reduced. So because we are not invoking the Fibonacci of 4 there. Okay. So only we are invoking, and when you are calling the first time here, you are not invoking that particular one. So it means drastically you are reducing the time complexity. So how the drastically it is reduced is the same kind of sub-problems are repeated several times. When you take n equals to 100, so you cannot imagine that number. So that many sub-problems which will be overlapped. Okay. So that is what the difficulty is this one. So it will be generated 2 power 100 function calls. So 2 power 100 function calls is reduced by using only 100 function calls. Okay. So here also what you can do it is simply look at it. So only this blue color is function calls. Remaining all are you are getting from the table. So if you look at the table also, so how this table is maintained is, if you take here, so for Fibonacci, I am storing the results. So 0, 1, 2, 3, 4, 5, 6. Okay. So in the first time there is no way is there, we need to do that particular one. Like Fibonacci of 6 is invoking Fibonacci of 5, Fibonacci of 5 is invoking Fibonacci of 4, and 4 is invoking 3, and 3 is invoking 2. After 2, 2 is invoking Fibonacci of 1. So Fibonacci of 1 is giving 1. I am storing in the record, I am storing the results, and Fibonacci of 0 is giving 0 here. Okay, then after this, once again when you are invoking from the Fibonacci of 3 to find the Fibonacci of 3, okay, so you need to invoke Fibonacci of 2. So Fibonacci of 2 is given as a 1, and then Fibonacci of 3 is nothing but the stored value 1 plus the whatever that value. So 2. In 3 we are getting 2. So for a 4, Fibonacci of 2 is giving 1, and Fibonacci of 3 is giving 2. So it is become a 3. It is become a 5. It is become a 8. Okay. So that is how it will work. So in order to find the Fibonacci of 6, you need not invoke the Fibonacci of 4 here. That 4 value is already available in the table, already it is available, so that you need not expand the entire tree. So whatever the green color nodes are there, these nodes functions are not invoked. These values are retrieved from the table because the values are already it is available in the table. So I need not call once again the same function. Okay, so this is what the dynamic behavior of your program. So why I am saying a dynamic is, here also you are saying a fib of 4, and here also you are saying a fib of 4. But here the function is invoked, but here the function is not invoked because the value is retrieved from the database. The value is retrieved from the database. So that is what the dynamic behavior of your program. So because of this dynamism, we are reducing the complexity drastically. Drastically, we are reducing the time complexity. You can observe in the Fibonacci series, if there is a n equals to 100, then you need to do 2 power 100 function calls. So 2 power 100 is a very big number. You cannot write in your classroom also on your walls if you are writing. That walls are not sufficient to write such big number. Okay, but that 2 power n is automatically reduced to order of n because only how many function calls you are calling? Only here n function calls only. Okay, so this is the benefit we are getting in the dynamic model. Whereas in the divide and conquer model, it is blindly divided and every time it is repeated. The same subproblem is solved several times. Okay, but whereas in dynamic model, because of its dynamic behavior, it won't invoke all the functions which are there. Okay, so this point is very important. You need to understand this particular point to solve all the problems in the dynamic programming model. Okay, so here if I want to find a Fibonacci of 6, so actually I am not directly solving the Fibonacci of 6 here. So first I am starting with Fibonacci 0 and then Fibonacci 1, then 2, 3, 4 like this. First I am solving the small subproblems, then I am coming to the actual problem. Okay, so in order to solve this particular problem, first I am solving the smaller one 0, 1, 2, 3, 4, 5, then I will come into the 6. It means bottom up approach. So small to bigger problem. But whereas in the divide and conquer, your bigger problem is divided into smaller pieces. But whereas here in the dynamic model, when you are writing the algorithms, you are not coming like in the forward way, which is very complex. So you are coming from the small sub problems to the big problems. Okay. So this point is also you have to remember in a dynamic model. So always in the dynamic programming, first we are solving the small problems, then followed by the bigger problems. Okay. So that you will be getting so much advantage. Is it point is clear for everyone? If you have any questions, you can ask now. Okay. So I'm giving 1 minute time. So this concept is very important. So just look at this problem and try to understand what do you mean by a sub problems overlapping. When sub problems are overlapped, so how the time complexity is reduced in the dynamic model and why it is not reduced in the divide and conquer model. So any questions you can pose it. So total 505 students are there, so very less attendance. Out of 800 students, only 500 students are present. If you have any questions, you can raise it so that we'll go to the next step. So this is the difference between a divide and conquer model and a dynamic model. In both the cases, the problems are divided into a subproblem, but here in dynamic programming, all these subproblems are overlapping, or most of the problems are overlapping with each other. But whereas in the divide and conquer model, all the subproblems are disjoint subproblems. Disjoint means there is no overlapping. Okay, so that is what the difference between this one. Okay, so some questions. No, not always we will get order of n. We'll see it. So it depends on the problem. So this actually nobody takes this as a dynamic problem. This is only to understand you how the problems are overlapped and how we are going to solve the problem. But by using a dynamic programming, we are solving the complex problems. For example, there is a problem is called a traveling salesperson problem is there. So where we need to find a closed path which covers all the cities exactly once. Okay, and such path should be the optimal path. And if you look at how many number of closed paths are there is, if you take a fully connected graph, you will be getting n factorial closed paths you are getting. So n factorial means it is not like a small number. If you take n factorial of 10 or 12, you can understand what is the difficulty with this one. Okay, when there are 100 cities are there, 100 factorial, you cannot imagine such big number. You cannot store in a machine also. Okay, it's a very big number. So these n factorial complexity is reduced to 2 power n. So 2 power 1 n is very lesser than n factorial. Okay, so that anyhow you will be getting always. So this is only a small one. The time complexity of the Fibonacci number is, you know that it is the order of n only. Okay. Now just look at some theory part of this one. So the difference between a dynamic programming and divide and conquer, most of the points I think covered. The first point is in the divide and conquer, the partition a problem into independent smaller subproblems. Okay. So generally the divide and conquer, the problems that you know in the divide and conquer, like whatever the merge sort or Station's matrix multiplication or whatever convex cell or whatever the problems you take. When you are dividing, the subproblems are a disjoint subproblems. The subproblems are a disjoint subproblems. Okay. But whereas in the dynamic model, partition a problem into a overlapping subproblem. So you will be getting most of the problems are overlapping. So when you are getting a overlapping, we are taking the advantage of the redundant subproblem and we are solving and we are reducing the complexity, time complexity. That is the first point. The second one is does not store solution of subproblem. So identical subproblems may arise. Results in the same computations are performed repeatedly. Okay. So actually divide and conquer don't know that whether the subproblem is a duplicate problem or the new problem. Okay. So it simply divides and it will solve it, whether the same problem is repeated or not. Okay. So but whereas in this one, it stores the solution of a subproblem. Whenever you are solving the new problem, it stores the result so that it will be reused the same value many times. That is the difference. Okay. So the third point is it is a top-down algorithm. So big problem is divided into smaller ones. But whereas in the dynamic model, first we are looking the small problems, then we are constructing the main problem. Okay. From smaller to the bigger problem we are going. Here it is from bigger to the smaller problem. Okay. So both will have a different approach and both will use it to solve the different problems. It is not like that you can solve by using dynamic programming all the problems like in divide and conquer. Okay. So divide and conquer problems are different and these problems are different. Okay. Next. Again, so there is again comparison between a dynamic and greedy method also. Yeah. So the first one is dynamic programming is used to obtain the optimal solutions. So this greedy method is also used to find the optimal solutions only. So both models are used to find the optimal solution or best solution. So both are same in this way. Okay. The second one is in dynamic programming, we choose at each step, but the choice may depends on the solution to a subproblem. See here, in dynamic programming actually, what exactly we are doing is, the whatever decisions you are taking, it is not the error-free decisions, or it is not 100% correct decisions in dynamic model. In dynamic, what we are saying is, so it is changing with the steps. Whereas in the greedy model, what is your observation is, the whatever decisions you are taking, it is a error-free decisions. It is a error-free decision. It means you look at the greedy problems. In every step, we are picking the item, and if you are getting a feasible solution, then you are adding to the solution. Otherwise, you are rejecting. It means in every step, the whatever decision you are taken, you are sticking to that particular decision. If it is selected, it is selected only. If it is rejected, then you are not once again reconsidering that rejected items. Best example is you take the Krishkal's algorithm. In every step, you are picking the least cost edge and you are adding to the solution if it is forming a feasible. Otherwise, you are rejecting. So once you rejected, you are not relooking that particular item, as well as if you are selected, once again you are not replacing with some other item. That is the specialty of the model. So the decisions which you have taken is the error-free decisions. But whereas in dynamic model, actually the whatever decisions you have taken, it is not error-free decisions. The decisions will change. Initially, you will said that it is accepted, but after some time, you will be saying that the whatever previous decision you have taken, it is wrong. Let us change that particular decision. It means, in other words, you can say in dynamic model, you will be getting a many sequence of decisions, whereas in the greedy model, only one sequence of decisions you will be getting. So in dynamic model, you are getting a many sequence of decisions because you don't know which one you are selecting, which one you are not selecting. So dynamically you are changing your decisions. But whereas in greedy model, the decisions are standard decisions, error-free decisions. Okay, so that is very important point you need to understand. Okay, so you may be saying that, sir, can't we take a error-free decision? You cannot take error-free decisions in some problems. Maybe the problems which we discussed in the greedy model, you can take error-free decisions, but whereas the problems that we are discussing in the dynamic model, we cannot take the error-free decisions. The decision we cannot tell at this point. Okay, so that is what you need to understand. The third point is, it is guaranteed that dynamic programming will generate an optimal solution using a principle of optimality. So by using dynamic programming, your decisions are dynamic, and finally you can conclude that this is the optimal solution for this particular problem. But whereas in the greedy model, there is no such guarantee. They are saying actually this point is wrong. Actually, it is not that. It's not like a guarantee actually. So these kind of problems, the greedy model cannot be applicable actually. So when you are when you are unable to take a decision, then you cannot apply a greedy model. I'll tell you the why you are getting this situation. Even in our life also, sometimes we are unable to take a decision. We'll be in dynamia. Okay, so maybe the decision is corrected in the latter stages, but whereas in the greedy, you have to take a decision. So that will not work for all the problems. That will not work for all the problems. Okay. So the example of a Dynamic model is there are many examples are there. So one simple example is 0 1 knapsack problem. What is the 0 1 knapsack is either you are taking the complete item in the bag or you are rejecting the complete item. But whereas in the fractional knapsack you are taking the item partially. Okay. So these are the two examples they are given. So if when you are comparing with greedy with dynamic, so both will have the same kind of problems. It looks like the same only. There are n objects are there. So the solution is also a subset of that n object. But the difference is in dynamic programming, the decisions are many sequence of decisions are generated, and finally we are concluding the optimal solution with the help of a principle of optimality. Principle of optimality. But whereas in the greedy model, we are generating only one sequence of decisions. Okay. Yeah, the examples of a dynamic programming is 0 1 knapsack problem, trialing salesperson problem. Okay. If you look at the trialing salesperson problem, so the time complexity of the trialing salesperson problem is n factorial closed paths you are getting. If it is a 100 city problem, and if you want to find a closed path which covers all the 100 cities, your machine is going to take at least 1 year to compute that particular problem. Or in other words, it is impossible to solve that particular problem if you are looking at n factorial closed paths. Okay. But if the same problem is addressed in the dynamic model by using the time complexity, it is order of 2 power n into n cube. Actually, it is order of 2 power n. So order of 2 power n is also it is not a small one, but when compared to the n factorial, it is very less. Okay. So this trialing salesperson problem still it is under research only. You can find many papers on the trialing salesperson problem. So because the difficulty of that problem is like this. So optimal binary search tree, these are all very highly complex problems. Okay. So this is what the introduction to the dynamic programming. If you have any questions, you can ask so that we'll go for the next topic. So this is what I gave the introduction to the dynamic programming actually. So there are two approaches you should observe. One is when you are looking the divide and conquer model. When you are looking the divide and conquer model, so the dynamic model is also like similar to your divide and conquer. But the thing is, dynamic model problems, the sub problems are overlapping. So when it is overlapping, solve one time, use many times. That is one principle you have to observe. The second one is in dynamic model, you are not taking a one sequence of decisions for given problem. You are taking a many sequence of decisions to solve that particular problem. These are the two things you need to observe for all the problems. Okay. So any questions from your side? You can put it. If no questions are there, we'll go for the next session. Any questions? So like this problem, we'll okay. Yeah, some problems are 2 power n also, but the actual time complexity is drastically reduced. Anyhow, that you will be looking for all the problems. You can imagine, you cannot imagine 2 power n is a very high. So that problem is drastically reduced to order of n square. So order of n square is which is lesser than 2 power n. You can take n equals to some value. Any other questions? Yeah, why the attendance is very less? So this is very important topic. Once again, I am telling. So those who are missing the topic, it is very difficult for them to understand. Any questions? Okay, then I'll go to the next session. If no questions are there. Yeah, this problem you need a lot of attention actually. The problem is OBST. So what is this OBST is optimal binary search tree. So we know a binary tree. What is a binary tree means? A binary tree is nothing but it is a set of nodes. In this node, one node is defined as a root node and all remaining nodes are divided into a disjoint subsets are called left subtree and the right subtree. This is what a binary tree definition. And what is a binary search tree is, it is a binary tree and based on the condition we are constructing the binary tree. What is the condition is, any element which is lesser than the root element should belongs to the left subtree and any element which is greater than the root element should belongs to the right subtree. So that is how the binary search tree is constructed. Okay. For a given element, you can construct the binary search tree. So how many binary search trees you can construct? So definitely it is, you can construct more than one. So when there are multiple binary search trees are there for given same data, then which tree is the best tree? That question will come. Okay. So what do you mean by a best tree actually here? So the best tree is a tree which takes the less number of comparisons. A tree, because the purpose of the binary search tree is searching the element in the tree. So why we need to search it? Because to access randomly the data, we need to use the binary search trees. Already you know that what is a binary search tree, all these things. Okay. The COBOL is a language, you know that it is using a binary search tree to search the database. Okay. So the COBOL is a language which is very popular language. So look at the first slide, optimal binary search tree. I think he has given the definition of the binary search tree. A binary search tree is a binary tree. First of all, it is a binary tree and either it is a empty tree. Any empty tree is a binary tree only or binary search tree also. Okay. So each node in the tree contains an identifier and all identifiers in the left subtree of T are less than. That is what I said. And all the identifiers in the right subtree of T are greater than. Okay. So that is what the binary search tree. I need not explain that particular one because this problem is very big. It requires a lot of time to understand the problem. Okay. So look at the right side bottom. There is an example of a binary search tree. So here 55 is the root. Any element lesser than the 55 is belongs to the left subtree. So the left subtree contains a 12 and 35. So among this 12 and 35, again the 35 is chosen as a root node. So again the left subtree will have 35 and 12. So 35 is a root. Again 12 is a less than the 35, it belongs to the left subtree. So similarly, you look at the right subtree of a 55, which contains a 68, 61, 92, which are greater than 55. This is applicable recursively for all the subtrees of your binary tree. So this is what the binary search tree. Okay. Any questions about this one? So this concept already you know in the data structure. So look at the simple example here. So there are three elements are there. So I have taken A1, A2, A3 is equals to 10, 20 and 30. So by using a three nodes, I can generate many trees. So there is a mathematical formula is there to know how many trees we can generate it. Okay. So here if you take a simple three elements binary search tree, I can construct total 5 binary search trees for given 3 elements. Okay. The first one is the left side if you look at, so I am taking the 10 as a root node. So the first I am taking the 10 as a root node. If I take a 10 as a root node, how many trees I can construct? I can construct the 2 trees. One is a 10 is a root node and the right subtree contains a 20 is a root node. So right subtree contains 20 is a root node. Yeah. So this is 10 is a root node and the right subtree contains 2 elements. Again for these 2 elements, right subtree contains the 2 elements. Again among these 2, I can select any one as a root element. If I select the right subtree root is 20, the tree is like that. If I select the 30 is a root of the right subtree, then the tree is become like this. So this is the 2 trees I am getting, and here if I select the 20 as a root element, if I select the 20 as a root element, any element lesser than the 20 should be there at left side, and any element greater than the 20 should be there in the right side. So because only there are 3 elements are there, so left side contains a 10 and right side contains a 30. So I can generate only one tree with the root equals to 20. So similarly, so when the root is 30, so I can generate another 2 trees, total 5 trees I am getting. Okay. So this is what a different trees we are constructing. So when there are different trees are there, what is the difference is here? If you look at, so now let us find out for each tree. So let us compute what is the cost that is involved here. So the purpose of the binary search tree is I want to search a key which is there in the database or which is there in the binary search tree. So suppose if I take the first tree is this one I am taking. If I take the first tree, then how many comparisons are required to search the 10 element? Because the 10 is there as a part of the root now, how many comparisons are required? Only one comparison I can tell that the 10 is available or not. If I want to looking for a 20 for the first tree, I need a 2 comparison because I need to compare the 10 and after that I should come to the right subtree again 20. So 2 comparisons are required to compare the 20 in the first tree. Then to compare the third, to search the 30, so what is that I am getting? 3 comparisons. So overall, how many comparisons are required if I access the elements 10, 20 and 30? So how many comparisons? For 10 1, for 22, for 33. So total 6 comparisons are required to access all the elements one by one. So total elements are 3 and the number of comparisons are 6. 6 by 3 is given a 2. Similarly, if I select the second tree also, the number of comparisons you can see it. For 10 it is 1. For 20 we need a 3 comparisons. For 30 we need only 2 comparisons. Okay. So based on the level of that particular item. So the level is going to define the how many comparisons are required. If you take in the second tree, if I take a 20, so it requires 3 comparisons because the level of 20 is a 3, location 3. So that is what we need to understand. But when you are going for the third tree, in the third tree, the number of comparisons, that is for 10 is 2, for 20 it is 1, for 30 it is 2. So total 5 comparisons are enough to search the 3 elements. What will be the average is 1.66. Okay. So like if you look at all the elements, all the trees that can be generated, by using a same set of elements. So which tree is giving a less comparisons is, you can observe that and you can see clearly that when it is compared to the other trees, this tree will have an advantage when compared to the other tree. So this is what you need to observe. When there are multiple trees are available, when there are multiple trees are available, so which tree is more promising for us, or which is the optimal subtree or optimal binary search tree is the tree which takes the less number of comparisons. Okay, so in this scenario, if all the elements are accessed exactly one time, then the middle tree is the best tree. But this is not always true, because if you take these key elements in a banking application and for account numbers, if it is a current account number, then frequently it is accessed. If it is a saving bank, rarely it is accessed when compared to the current account. If it is a fixed deposit, very rarely we'll access. So it means the keys which frequently we are accessing, the key which frequently we are accessing must be there at the top. That is how the red block trees and AVL trees, which are used to maintain maintain to reduce the number of comparisons. Okay, so this is basically the OBST is the final optimal solution of that particular problem, the best solution among all the trees. Okay, so here also if you look at the same problem is explained, but the difference is the 10 key which we are accessing every day 3 times. The frequency of accessing the key 10 is 3 times. The frequency of accessing 20 is 2 times. The frequency of accessing 30 is 6 times. It means a customer who is having account number 10 is daily is visiting 3 times to access his account. Similarly, a customer with 20 account number daily he will be coming 2 times. So a customer with 30 account number is coming 6 times a day. Okay, so it means every time you need to perform the search operation to identify to find the data of a particular customer, like what is the current balance and everything, whatever the information which is required. Okay, so in this case, if the same 5 trees I am using, because there are 3 elements are there, and I can generate a 5 different binary search trees, and what will be the total cost of the each tree is, let me compute the first tree so that other things you can do it. Okay, if I take the first tree, the root is 10, so how many times 10 is accessed? So only 3 times per day. 3 into how many comparisons? Only one comparison is enough to identify the 10 for the first tree. I am talking about the first tree. So 3. For accessing 20, so 2 comparisons are required and frequency is 2. So 2 into 2 is equals to 4. Similarly, for a third element, 6 into 3 is 18. So total the number of comparisons which are required to fulfill the given data is 25 comparisons are required if I am using the first tree. If I am using the second tree, it is 21. If I am using a third tree, it is 20. Then fourth, fifth. So which is the best solution for given these frequency values is this particular tree. Previously, the middle one is the highest priority, but now the scenario is changed here. Here the 30 is the element which is frequently accessing, so we must ensure that the 30 key should be there at the root element so that you can access many times with no time. So here this is what the scenario. So what is the best solution is 18. Okay. Any questions till this? Okay. If you have any questions, you can ask now. I'll give 1 minute time to you. So if you have any questions, please ask. This is actually the old story only. It is not a new story. So already you have seen in your regular binary search classes. So now what is the problem with this particular one is, given a key elements, the key elements are 10, 20, 30 like this, given a key elements and its frequencies, or in some other words I can say the probability of occurrence, the probability of the occurrence you can give in terms of probabilities also. So another very important point you need to understand is, the values are 10, 20 and 30. Sometimes a customer will come and he will try to search the data of 5. He'll try to, what is the information of the customer whose account number is 5. So, but is it 5 is there account number? It is not there actually. It may be deleted long back. But somebody came and is trying to search whether the what is the information of the account number 5. So, if I give the 5 for the first tree, how many comparisons are required to tell that 5 is not there in the tree? So, in this case, I need only one comparison for telling that 5 is not available in the first tree. The second one is also only one comparison I can tell. For third one, how many comparisons are required to tell that 5 is not there? First I need to compare with 20, and 5 is less than 20. I need to go to the left subtree. Again I need to compare with the 10. So I need to go to the left subtree. So for 10, there is no left subtree is there. So to tell whether the 5 is not available in the tree, I need to perform a 2 searches, 2 comparisons. So similarly, here also 3 comparisons. Here 2 comparisons. So this is also may occur in the tree. So always we are not searching the elements which are there in the tree. Sometimes, maybe it is rarely, we may give a key which is also not there in the database. So for that also it has to do some work, because without searching you cannot give the result saying that a particular element is available in the tree or not. I have taken the example is a 5 is the example. You can take any element which is not there in the tree and you can see how many comparisons which are required for that one. Okay. So this you leave it. So this theory part. Now let us take the example. Any questions? Fine. No. Okay. Optimal binary search tree, the problem. Okay. So there are n identifiers are there. That is A1, A2, A3 to A1. These are the key elements are there. In this example, we have taken A1 is a 10, A2 is a 20, A3 is a 30. Okay. So for every element, they are given a probability. That is, let P of I be the probability with which we search for A of I. It means whatever the key elements are there, for every key element, I am giving the probability. The probability will tell that how frequently that element is accessed. How frequently the element is accessed. That is what the probability of the key elements. At the same time, I am also giving a probability of unsuccessful search also, like Q of I. So Q of I is nothing but the probability with which we search for an identifier X such that A of I X is, which is A of I is less than X and less than A of I. Okay. So this point is very important. You need to understand. So now let me take this slide to give more clarity. Yeah, here the identifiers are 30, 20 and 10. That is there in the oval shape. Okay, but there is a rectangle boxes also you can observe. What is this rectangle boxes is when you are looking for an element which is not there in the tree. So that time your search will be terminated at one of the points, that is from E0 to E3. So now I want to search for a 5. Then 5 is which is less than 30, come to the left side, and 5 is less than 20, come to the left side, and 10 is less than 20, come to the left side. So after 3 comparisons, then the 5 is terminated at this location. The 5 is terminated at this location. Let us take a 7. 7 is less than 30, less than 20, less than 10. 7 is also terminated at the same point. Let us take 11. I want to search for 11. So 11 is less than 30, come to the left side. 11 is less than 20, come to the left side. And 11 is greater than 10. So come to the right side. So 11 is terminated at this location. Okay. So similarly, if you take from minus infinity to, if I write it, any element from minus infinity to 9, if I am taking an integer, will terminate at E0. Any element between 11 to 19 will terminate at E1. Any element which is 21 to 29 will be terminated at E2. If you want, you can check it by taking one example. For example, I want to search for a 25. So 25 is less than 30, come to the left side, and 25 is greater than 20, come to the right side. So right side nothing is there. It is a null value. So these rectangle boxes are not a part of the tree. But when you are searching the elements which are not there in the tree will terminate at this point. Okay. So similarly, if you take E3, any element from 31 to plus infinity, all the elements which is more than 30 will be terminated this one. Okay. So that Q naught or Q is nothing but this Q of I is the unsuccessful search. It is the probability of giving a key element which is not present in this one. Okay. So that unsuccessful search also is divided based on the values, because all the values don't need the same comparisons. All the values don't need a same number of comparisons. If I am searching for a 5, I need a 3 comparisons. But if I am searching for a 35, I need only one comparison. There is a difference between the number of comparisons. Okay. So this point you need to understand from this particular diagram. Okay. And another one, when there are 3 key elements are there, how many non-key values are there or how many non-nodes are available. Here it is E0 to E3. It means if this is A1, A2, A3, then definitely you should have the E0, E1, E2, E3. So it means there is one more extra virtual node is present when n equals to this one. If n is the number of key elements, then n plus 1 virtual nodes are there for any binary search tree. Okay, so we must consider these elements, the terminal and non-terminal, or real nodes or the virtual nodes. Rectangle boxes are nothing but the virtual nodes, and the circle is real nodes. Then how do you compute the cost of the each element is, you can observe in the formula, mathematical formula they are given. If it is a key element, that is A of I is nothing but it is a key element. Okay, so how to compare the key element is, so P of I means how many times the A of I you are accessing, the probability of A of I, that is P of I, into level of A of I. Level will define the how many comparisons are required. Suppose if you take a 10, it is at level 3. So this is a level 1, this is level 2, level 3. So it is based on the how many comparisons which are required. So if it is a key element, the number of comparisons are based on the level of that key element. So that is what the first one. The second one is, if it is a virtual node, then actually this node is not available on the tree. It is a virtual node because the right part of the 30 is a null value. So there is no such node is existed in the binary search tree. So but still we need to do the comparison. So that's why for unsuccessful search we need to use Q of I is nothing but how frequently that node, virtual node is accessing into level of EI. What is the level of EI? It is a 2. But for level of 2, we need only one comparison. Okay. So that's why level of I, EI minus 1. Whereas this is directly level and this is minus 1. Okay. So why it is minus 1 is, you observe here, let us you are looking for a 35. How many comparisons? Only one comparison you need to do it. So E3 is available at level 2, it means it must be minus 1. So by using this mathematical formula, you can compute the total number of paths. So this point is clear for everyone? So this is very important, you need to understand. When there are n key elements are there, so we need to look at n plus 1 virtual nodes. This is another one. Your time is very less, so I need to move fast. Yeah. This other one is, suppose if I select the A of K as a key element, then what is there in the left subtree and what is there in the right subtree? Is the left subtree contains all the elements which are lesser than the key element. So A of K is a key element. It means all the elements which are lesser than the key element, that is from A1 to A of K minus 1. Similarly, what is there in the right subtree is A of K plus 1 to A of N. So these are the elements which are there in the left subtree. So provided all the elements A of 1 is less than A of 2, less than A of 3, less than A of K, less than A of N. So it means all the elements are it is in sorted, so that we can divide the tree like this. If I am choosing the AK as a first element, root element, the left subtree contains A12 AK minus 1, A12 AK minus 1, and the right subtree contains A of K plus 1 to AN. So A of K plus 1 to AN elements are there. Here it is A1 to A of K minus 1. AK is the root element. So not only the key elements, the virtual nodes is also divided into two parts. That is Q0 to Q of K minus 1. That is nothing but E0 to E of minus 1. Virtual nodes are there in the left subtree. The right subtree contains E of K to E of M. Okay. So this is divided, and we need to compute the total number of comparisons. The total number of comparisons is depends on the total cost is depends on P of K, the probability of accessing A of K, plus the cost of the left subtree. The cost of the left subtree means this one. This particular part is a cost of the left subtree, and cost of the right subtree. See it here. So the total cost of the trees can be defined. The probability of accessing the first that A of K element, that is a P of K, plus the cost of the left subtree, plus cost of the right subtree, plus how many times accessing the left subtree, this one, how many times you are accessing the right subtree is this one. Okay. So that can be represented by using in mathematical formula, that is P of K, the probability of the kth element, plus the cost of the left subtree is nothing but C of 0 to K minus 1, and the cost of the right subtree C of K comma N, and cost of the weight of the left subtree is weight of the right subtree. Okay. So that is what you need to understand. So if I am selecting the AK as a root element, then the left subtree contains these are the values, and the right subtree contains these are the values. These are the key elements. Okay. So for which value of K I am getting a minimum number of comparison, that is what we need to find out. So what is the formula is the cost of the total tree, that is C of 0 comma N. C of 0 comma N. So let me explain quickly for this one also. If I take C of 0 comma N, this is nothing but your entire tree, which contains A1 to AN terminal nodes and E0 to EN non-terminal nodes. This is your entire tree. Then what is there in the C of 0 comma K minus 1 is it contains A1 to A of K minus 1 and E0 to E of K minus 1 nodes. That is a left subtree. This is a left subtree. This is a right subtree. So what is there in the right subtree is, if you take this particular one, then it contains A of K plus 1 to A of N and E of K to E of N. Okay, because always one extra node will be there in the virtual node, so that's why it will be like this. So this you need to understand. Okay, the same this one. This is basically tells the cost of the entire tree. But now the cost of the subtrees, that is C of I comma j in general, C of I comma j is equals to minimum of C of I comma K minus 1 left subtree plus the right subtree. Okay, so this is what the mathematical formula. So it will take to understand this one. Yeah. So let me explain the problem here. So remember your Fibonacci tree. Okay. Let me explain the problem. So here let n equals to 4 and the values are a1, a2, a3, a4 is the key elements, and he has defined as a do, if, int, while. These are the key elements are there which are in sorted order alphabetically. So here the key elements are do, if, int, while. So that is what your key elements in the binary search tree. You can take the values also like 10, 20, 30, 40. That is your wish. Okay. So now he has given the p-value. The p-value is basically will give the how many times each key element you are accessing, the frequency of the each key element. For example, how many times your A1 you are accessing is 3 times. How many times A2 you are accessing is 3 times. How many times A3 you are accessing is only 1 time. A4 1 time. Similarly, how many times you are accessing E0? E0 means any alphabet word which is less than the do comes under that one, E0. So E0 is 2 times, E1 is 3 times, like this. All these are unsuccessful search. So these probabilities of successful search, these probabilities are unsuccessful search, how frequently you are accessing. Okay. So here, if you add up all these frequencies, 3 plus 3 is 6, 6 plus 2 is 8. So 8 successful search you are performing, and 3 plus 2 is 5, 5 plus 3 is 8. 8 unsuccessful search you are finding. 8 successful search, 8 unsuccessful search. Total 16 searches you are performing. Okay. So here you need to construct the binary search tree, which is an optimal binary search tree. Okay. So here the cost of 0, 4 is nothing but the total cost. Okay. The total cost of that particular tree is divided into 4 parts. Why it is divided into 4 sub-problems is, if I select the A1 as a root element, if I select the A1 as a root element, then the left subtree contains only one node, that is E0. And what is there in the right subtree? The right subtree contains A2, A3, A4 and E1 to E4. If I select the A1 as a root element, this is what I represented here. Similarly, if I select A2 as a root element, then the left subtree contains A1 and E0 and E1, and the right subtree contains A3, A4 and E2 to E4. Similarly, if I select this particular one, why I am getting this combination? If I select the A3 as a root element, then the left subtree contains A1 and A2 and E0, E1, E2. Right subtree contains A4 and E3, E4. Similarly, if you take this particular one, if I select the A4 as a root element, the left subtree contains A1, A2, A3 followed by E0 to this one, and right subtree doesn't have any nodes. Okay. See here, what is the cost I am getting if I select the A1 as a root node? What is the cost I am getting A2 as a root node? What is the cost I am getting if A3 as a root node? Okay, if you are going a top-down approach, it will be like this. Okay, so in divide and conquer model, we are going a top-down approach, but in dynamic model, you are going a bottom-up approach. So what in by a bottom-up approach is, first solve the small problems. First, solve the small problems, small sub-problems, then you solve this one. Okay. So this is what you need to understand here from this example. here. So if you look at the same problem I have taken here, so now W of I comma I. So what is the W of I comma I? So W of I comma I doesn't have any nodes. It will have only one virtual node, is nothing but E of I. So that's why the probability is Q of I is given. What is the cost of the empty tree? C of I comma I is 0. So C of I comma I is a 0 because that is the empty tree. So R of I comma I 0 because there is no nodes are there. So that's why the first installation part is done here. And this formula is very important when you are solving the OBST. So W of I comma j is equals to P of j plus Q of j plus W of I comma j minus 1. Okay. So this is a recursive formula is there we are using in this one. Remember this formulas. Okay. So if W of 1 comma I comma I, the formula is this one. If W of I comma j, if I is not equal to j, the formula is this one. Okay. Now I need to compute a smaller t. Okay, I need to compute a smaller t. So that is W of 0 comma 1 is equal to P of 1 plus Q of 1 plus W of 0 0. So this formula actually is taken from this one. Look at this one. W of I comma j. I is 0, j is 1. Is nothing but P of j, Q of j. There is nothing but P of 1, Q of 1 plus W of 0 and 0. So this is what the total weight I am getting. So similarly, the cost of 0 comma 1 is nothing but the formula. So the formula is already the previous it is there. So if you want to look at the formula, so the formula is this one. So for every value you need to compute it. So here, in order to construct the optimal binary search tree, so first I am constructing the trees which contains exactly one node. First I am constructing the trees which contains exactly one node. How many subtrees I am getting which contains exactly one node is there are 4 different trees I am getting. Okay. So look at the first one. So the first tree. So first of all W of 0 1. What is there in the W of 0 1 is the W of 0 1 contains the A1 key and E0, E1. So these are the 3 items which are available in a subtree. A subtree which contains exactly one node. So the one node may be A1 or A2 or A3 or A4. That we don't know actually here. So now I need to compute the smaller problems first, then I need to go for a bigger problem. So in this example, if you just observe, so I am going to construct the tree which contains exactly one node. Okay. So here W of 0 1 is nothing but the how many times you are accessing this particular tree. So W of 0 1 means which contains 3 elements A1 along with the E0 and E1. So probability of 1 plus Q of 1 plus W of 0 0. It's nothing but 8. So C of 0 1. What is the cost of 0 1? Is W of 0 1 plus the minimum of C of 0 0 plus C of 1 1. So C of 0 0 is 0 and C of 1 1 is also 0. So because C of 0 0 means this particular one. This is nothing but C of 0 0. And this is nothing but C of 1 comma 1. This left right subtree. And A1 is a root element here. Okay, so here T of 1 1 is cost is 0 only because no elements are there. That is empty actually. E0 means it is physically it is not present. So that's why 0 and 0 and W of 0 1 value is 8. So the 8 value is stored. So the root, what is the root element in the subtree? A1 is a root element. So what is the total cost? If you compute manually also, you will get 8 only. If you want to compute, let me compute it. A1, how many times you are accessing here? 3 times. So how many comparisons for A1? 3 comparisons plus E naught. How many times you are accessing E naught? 2 times. How many comparisons for E naught? 1 comparison. That is 2. Again E1. How many times you are accessing E1? 3 times here. So 3 times means this is Q naught, Q1, Q2 like this. Okay. So plus 3 will give total 8. So the total cost of this particular subtree is 8. That's why T of 0, 1, which contains A1, along with the A1, you have E0 and E1. Okay. So which is the root element you are selecting here? 1 is a root element because there is no other elements are present. So similarly, I want to construct the tree which contains exactly one node, but this time the node is A2 node. Previously it is A1. So again, to construct the cost of the A2, W of 1, 2. So what is there in the W of N2? W of 1, comma 2. What is there in the W of 1, comma 2? It contains A2 is the one key element and E1 and E2 is the virtual nodes. Okay. So here also the W of 1, 2 is 7 and C of 1, 2 is equals to W of 1, comma 2 plus the minimum value of left subtree cost and the right subtree cost. This is left subtree cost, this is right subtree cost. Okay. So now the total cost is 7 and which is the root element in the small subtree which contains exactly one node is only 2 here. Okay. Yeah. Similarly, I want to construct the tree which contains exactly one node. Now this time it is a A3 is the root 1. The cost will be 3 here. Similarly, for a node which contains only one node, that is the A4 node. So the cost will be this one. So like this, we constructed the small trees which contains exactly one node. Now I am looking the tree which contains exactly two nodes, which contains exactly two nodes. So how many two node trees I can construct subtrees? Here A1, A2 is the one tree which contains exactly two nodes. That is what W of 0, comma 1. So 0, comma 2 is nothing but it contains, when I am saying is 0, comma 2, what is there in the tree? It contains A1 and A2 terminal nodes are the key nodes and E0 to E2, 3 virtual nodes are there. So by using these two nodes, I can construct the two different trees. But among these two different trees, the first subtree is this one, which I constructed this one. The next tree is this one, which I constructed this one. Okay. So now among these two trees, the left subtree cost if you add it, so you will be getting 0 plus 7. The C of 0, 0 is the previous values. Okay. So like this 0 plus 7, 8 plus 0. Similarly, and you are getting 7 and 8. Among the 7 and 8, which is the least one? 7 is the least one. For which tree you are getting a 7? This tree I am getting a 7. So it means I have selected among these two trees, which is the suboptimal tree. This is the suboptimal tree. This I am not looking. I am eliminating that one. Okay. Similarly, so I want to construct the tree of size 2. So this time the tree will have only A2 and A3. Previously it is A1 and A2. Now this subtree will have A2 and A3. Okay. So when you are computing the same values, which tree is the optimal one? This is the optimal tree. What is the cost of that one? The total cost I am getting is 12 here. If you do it manually also, you will get the same value. Again, the third tree, which contains exactly two nodes, that is the A3 and A4. Okay. So among these two, which is the optimal one? So this is the optimal one. So because this will give the cost is 8 and this will give the, of course, in both the cases, the cost will be 8. Any one you can select it, but I have selected 8. Okay. Now once that is over, again you are computing the higher level problem. So what is problem here? Again, I am going to construct the tree which contains exactly 3 nodes now. Previously, it is 2 nodes. So, how many different trees I can construct with exactly 3 nodes is I can construct this one. So, this one is the first tree, and this one is the second tree, and this one is the third tree. So if I select the A1 as a root element, because C of 0 comma 3 will have A1, A2, A3 and E0, E1, E2, E3. That is what C of 0 comma 3. It is a subtree. Okay. So here, if I select the A1 as a root element, what is the cost I am getting? If I select the A2 as a root element, what is the total cost I am getting? Similarly, if I select the A3 as a root element, if I select the A1 as a root element, I got it 12. If I select the A2 as a root element, I got it 11. If I select the A3 as a root element, I got it 19. So among these 3 trees, which is the optimal tree? Is the 11, which is giving a lesser value. So that's why I selected the middle tree, which contains the A2 as a root element. Okay. So again, in the similarly, there is one more tree you will get it, which contains exactly 3 nodes. That is A2, A3, A4. So previously it is A1, A2, A3, but this time it is A2, A3, A4. Again, among this one, so the first tree which is giving a less cost, so that's why I selected the A2 as a root element. Then finally, this is what the tree which contains exactly 4 nodes. So what is the value you need to compute? You need to compute C of 0 comma 4, which contains, what is there in the C of 0 comma 4? 0 4 contains A1 to A4 key elements, E0 to E4. This is your entire tree. Okay. So in this, if I select the A1 as a root element, then the tree will be like this. If I select the A2 as a root element, this is the combination I am getting. And if I select the A3 as a root element, A3 means here A, K value is changing here. So here the A4, here the A4 as a root element, here the A3 as a root element, here the A2 as a root element, here the A1 as a root element. So among these 4 combinations, which is a more promising? If I select the A1 as a root element, I got it 19 by using a mathematical formula. Okay, because these values already you previously computed, C of 0, 0, C of 1, 4. Okay, so now 16, 22 and 25. So which is more promising tree? If I select the A2 as a root element, then it is giving 16 and the total cost is 32. Okay, so this is what the table you need to generate it. Okay, so I'll take 2 more minutes. 45 already 5 minutes is late. So let me take 2 more minutes to explain the final tree. Yeah, now with the help of this particular values, okay. So now C of 0, 4, you look at here, C of 0, 4. So which contains all your nodes and everything. Okay. So C of 0, 4 is total cost is 32, and which element you selected as a root is this one you selected as a root. So that is I am selecting the A2 as a root element. If I select the A2 as a root element, A2 as a root element, the left subtree contains only one node, that is A1. So I added A1. But when you are going for a right subtree, the A3 and A4 is there. So W of 0, C of 0 comma 4, if you look at here, so C of 0 comma 4 in the slides. So C of 0 comma 4 is treated like C of 0 comma 1. The left subtree contains only one node A1 and the right subtree contains C of 2, 4. So what is the value of C of 2, 4? The value of C of 2, 4 is C of 2 4, where it is there? C of 2 4. C of 2 4 is here. So in C of 2 4, it contains A3 and A4. Root element you corrected. The root element is A3 as a root element. So the left subtree contains nothing, and the right subtree contains again A4, because A4 is greater than this one. Now here you can write down the E0, E1, E2, E3, E4. Okay. So this is what the optimal binary search tree for given this particular data. Okay. So this is what you need to compute it in order to give the optimal solution. Okay. Yeah, I think this is the table. So all of you practice it. It is not that much easy to understand the concept. Okay, so you practice more and more. Any clarification is required. So in the next class you can ask. So that I'll repeat. So no questions means